properties. I keep forgetting that my purple is lost ink. I just throw that one away. All right, new color. Properties of exponents. So let's do a small review. If we have a number raised to a power, okay, this thing up here is called the exponent. This is raised to the power of n, and it raises the base. Okay, so this a right here, that's the base. And then the whole thing together a to the n, that's called the power. Okay, so you have your exponent, you have your base, and the whole thing is called the power. Okay, so sometimes if you see an exponent, for example, if you see something like 3 to the second, you'll hear people say 3 to the second power. It's also 3 with 2 as an exponent, 3 squared. There's different ways to kind of say that, but in this case, 3 is your base, 2 is your exponent, and the whole thing is 3 to the second power. Okay, now we're going to get into what the properties of exponents are. Okay, and so what I'm going to do is I'm going to kind of show you a practical example first, then I'm going to show you kind of the general rule. Okay, so let's look at 3 squared times 3 to the 5th power. Okay, 3 squared times 3 to the 5th power. You'll notice that these two have the same base, and that's going to be important. Okay, when we're dealing with the same bases, we have some things that we can do. And I want to draw a distinction between that and this. Okay, because these are going to give us two different numbers. All right, so 3 squared, you probably know that that's 9, but what I want to do is I want to write that out. So this is 3 squared times 3 to the 5th. So 3 squared is just 3 times 3, right? The squared, the 2 up here, that exponent means how many times we multiply the base. Okay, that 2 simply means how many times we multiply the base. The base is 3, and we're going to multiply it 2 times. That's why 3 to the second power is 3 times 3. Now this, we're going to bring this times down here. And then 3 to the 5th power is 3 multiplying the base of 3 5 times. So 1, 2, 3, 4, 5. So we have 2 from this one, and then we have 5 from this one. Now look how many times we're multiplying 3 together. We're multiplying it 1, 2, 3, 4, 5, 6, 7 times. So another way that we can write this is 3 to the 7th power. 3 to the 7th power. Because I'm multiplying the base 3 7 times. So 3 squared times 3 to the 5th power is equal to 3 to the 7th power. Now, I worked that out to show you the first general rule, and that is when you have the same base, you can add the exponents together. 2 plus 5 is 7. So 3 squared times 3 to the 5th is equal to 3 to the 2 plus 5, which is 3 to the 7th. Okay? This is very important because what this allows us to do is rather than having to write this out over and over and over and then count them all up, we know that, hey, if we're multiplying things with powers, things with exponents, and they happen to share the same base, we can add their exponents, okay? So here's the rule. Here's your first rule. A to the n power times a to the m power is a to the n plus m. That is rule number 1, or the first property of exponents. Okay. All right. Now, let's look at that. Let's look at properties of exponents. Now, dividing. So let's use the same example. Okay, we'll say 3 to the 5th power divided by 3 to the 2nd power. Okay. So if we write this out, 3 to the 5th power, that 3 is going to be multiplied by itself 5 times. 1, 2, 3, 4, 5. We're going to divide 3 to the 2nd power. So that's going to be 3 times 3. All right. Now we notice here that we have 1, 2, 3, 4, 5 factors of 3 up here, 2 factors of 3 down here. So what's interesting here is that this 3 will cancel with this 3. And this 3 will cancel with this 3. So 3 over 3 is 1 times 3 over 3 is 1 times 3 times 3 times 3. So we're left with 3 times 3 times 3, because these cancel into ones, and 1 multiplied by anything is just that anything. So we don't write those ones, but 3 times 3 times 3 can be expressed as 3 to the 3rd power. Okay, so 3 to the 5th power divided by 3 to the 2nd power is 3 to the 3rd power. Now we notice another relationship. If these share the same base, I can subtract the exponents. 3 to the 5th power divided by 3 to the 2nd power is equal to 3 to the 5 minus 2, which is 3 to the 3rd power. Okay, okay, we had a few more people join. Let me update our roll here. We've got Vivian. Excuse me. And Jay. I already have James. James, I think you have come in twice every time. That's okay. All right. So that is going to bring us to our second general rule, and that is when we share bases and we are dividing a to the nth power divided by a to the mth power, that is equal to a to the n minus m. Right. So for those of you just joining, the first one was a to the n times a to the m is equal to a to the n plus m. All right. Okay, Now what I want to do real quick before we move on to the third one is show you why 3 plus, or 3 to the second power plus 3 to the fifth power doesn't follow these rules. So if I look at this, 3 squared is 3 times 3 plus 3 to the fifth is 3 times 3 times 3. 1, 2, 3, 4, 5. Okay. So this right here would be 9. All right. And 3 to the fifth power, let me think about that real quick. Actually, let me just plug that into my calculator. That's 243. That's 3 times 3 times 3 times 3 times 3. And if I add 243 to 9, I get 252. All right. Now, if I just multiply 3 by itself 7 times. All right, that's 2,187. 1, 2, 3, 4, 5, 6, 7. Okay, so you can see how these two numbers are definitely not equal. 2,187 and 252, they're orders of magnitude different. In other words, this is in the hundreds and this is in the thousands. So these rules that we're looking at are only going to deal with factors. They're not going to deal with terms. Okay. When you're dealing with terms, we will not be able to combine. And we should know that because these are not like terms, right? They have the same base, but they don't have the same exponent. Okay. All right. So here was our first rule. Here was our second rule. Now let's look at our third one. Our third one is going to be kind of an extension of this one. And I'm going to, instead of doing 3 to the fifth over 3 squared, I'm going to reverse it. I'm going to do 3 squared over 3 to the fifth. All right, now we know that we can subtract them because we've kind of proved that here, but I'm going to go ahead and write it out again just so you can kind of see this. So we're going to have 3 times 3 in the numerator. That's my 3 to the second power. And then here in the denominator, I'm going to have 3 to the fifth power. 1, 2, 3, 4, and 5. All right, so just like the ones down here in this example canceled into ones, so these will cancel into ones, okay? So I'm left with 3 over 3 is 1, 3 over 3 is 1. So I'm left with just a 1 in the numerator. And that time I will put a 1. Here, that 1 exists, but we normally, if we just have a 1 in the denominator, normally we don't write it unless we want to visually line up some fractions. Any number is understood to be over 1, or it can be expressed as over 1. Here, we'll have to put 1 in the numerator, right? You can't just write the number 3 for 1/3. You have to show that as 1 over 3. So in this case, we have 1 over 3 times 3 times 3. So that's 3 to the third power. Okay, now I'm going to apply this general rule here, okay, because it's still going to yield the correct answer, but I want you to see kind of what happens. So in this case, 3 to the second power divided by 3 to the fifth power is a to the top one minus the bottom one. So here, 3 to the 2 minus 5. Okay. So we have 3, and what is 2 minus 5? Well, that would be negative 3. 3 to the negative third power. Now, what does that mean that I have a negative third? Well, when we worked it out here, this is what it means. 3 to the negative third is 1 over 3 to the positive third. So when we have a negative in the exponent, we're going to have to move that to the denominator. And that brings us to our fourth rule, which is a to the negative n is equal to 1 over a to the positive n. And how do we know that? Because when we worked it out here, that's what we were left with. So that negative exponent will mean it's down there. Now, the inverse of that is also true, meaning that if I have 1 over, let's say, 4 to the negative second power, okay? Notice how this negative exponent, it's already in the denominator. In this case, 3 to the negative third was in the numerator, so we brought it to the denominator. So in this case, let's work this out. So I have 1 over this 4 to the negative 2. I'm going to move that 4 to the negative 2 into a little denominator here. So this becomes 1 over 4 squared in the denominator. And if I simplify this, I have the numerator times the inverse of the denominator, which is 4 to the second power over 1. 1 times 4 squared over 1 is 4 squared. Okay, so let's review that real quick because that was a little complicated. So here we had 1 over 4 to the negative 2. If we just look at that negative 4 to the negative 2, I'm going to put that in the denominator here, and now that negative is positive 1 over this. But notice that it already sits in the denominator of this fraction. So I can, if I divide fractions, I take the top number, I flip the bottom number, and multiply them together. That gives me 4 squared. So we see that 1 divided by 4 to the negative 2 is equal to 4 to the positive 2. So if I have a negative like I do up here in the numerator, it's going to bring that down here to the denominator. 3 to the negative third is going to be 1 over 3 to the positive third. If it exists in the denominator with a little negative, 1 over 4 to the negative 2, then it's going to bring it to the numerator, 4 to the positive 2. So a to the negative n is equal to 1 over a to the n, and then 1 over a to the negative n is equal to a to the positive n. Those are my next two general principles. All right. Okay. Now, there was a question that was asked, I think probably week 2 or 3, and I kind of explained it at that time, but we hadn't really studied exponents yet. And so now we're going to start that. And that question was, if you have a number raised to the 0 power, why is that the number 1? So we're going to look at that now. So if we have 3 to the, let's say, 4th power divided by 3 to the 4th power, okay, what is that? Well, the numerator is going to have 3 to the 4th power, so the base 3 multiplied 4 times, 1, 2, 3, 4, divided by the base here, the exact same thing, base of 3 multiplied 4 times. Well, watch what happens. This 3 and this 3 cancel. This 3 and this 3 cancel. And they all cancel into 1. So you basically have 1 times 1 times 1 times 1. So that just leaves you with the number 1. Now, if we apply that second rule, remember that second rule that we looked at, a to the n divided by a to the m is a to the n minus m. So in that case, we can do 3 to the 4 over 3 to the 4 is equal to 3 to the 4 minus 4. 4 minus 4 is 0. 3 to the 0 power yields the number 1. So now you have a little bit more context, a little bit more knowledge in why this phenomenon is the way that it is. So the general rule of to the 0th power is a to the 0 power is equal to 1. And that a, it's a variable, represents any base. That could be the number 12, the number 7,000, the number -5. It doesn't matter what that number is. If it's raised to the 0 power, it'll just be the number 1. All right. Now our next property that we're going to look at, we're going to look at 3 to the 3rd power raised to the 4th power. Okay? 3 to the 3rd power raised to the 4th power. Okay. So here, let's look inside the parentheses first. 3 to the 3rd power, that is 3 times 3 times 3. 3 to the 3rd power, the base 3, multiplied 3 times. But I want that whole quantity raised to the 4th power. So what that means is I'm going to have 3 3's multiplied by 3 3's multiplied by 3 3's multiplied by 3 3's. Okay. 3 times 3 times 3. There's my first one. 3 times 3 times 3. That's my second one. 3 times 3 times 3. That's my third one. 3 times 3 times 3. That's my fourth one. Okay. Well, here, the parentheses just mean I'm multiplying. There's no addition or subtraction, so there's no having to distribute. There are no terms here. It's all factors. So I can multiply all this out. So I have 3 times 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 3. Then my fourth one times 3 times 3 times 3. Okay. That came from the first set of 3's multiplied by the next set of 3's multiplied by the next and the next. Here are the 4 sets that are in here. And then these 3 3's come from this 3 to the 3rd. Okay. So how many 3's do I have here total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is 3 to the 12th power. Okay. So what we've just proved here is 3 to the 3rd power raised to the 4th power is 3 to the 12th power. In other words, when you have an exponent raised to an exponent, what you can do instead of adding them or subtracting them, in this case, where we have an exponent raised to another exponent, we multiply 3 to the 3rd times 4. And that is 3 to the 12th. Okay. So to generalize this statement, we have a to the nth raised to the mth power. That is a to the n times m. Okay. All right. So what I'm going to do now is make a little list of all of our different properties. Okay. Base a to the n times a to the mth is equal to a to the n plus m. A to the n over a to the mth is equal to a to the n minus m. I'll do it down here. A to the negative n is equal to 1 over a to the positive n. And 1 over a to the negative n is equal to a to the positive n. Draw a line in between these two just to bring clarity there. A to the 0 is equal to 1. And a to the nth raised to the mth power is equal to a to the n times m. All right, let me double check, make sure that I have covered all of the properties that I want to cover. Okay, good. So now what I'd like to do, and this is kind of a handy thing to write down on a piece of paper while you're doing your homework to kind of reference back to on how to do some of these. Because we're going to start working a few problems so that you kind of get good at this. All right, so let's do this. And we're going to introduce variables into this too. So if we have x to the third times x to the fourth, what is that? Well, I have similar bases, so I can combine these by adding them. This is x to the 3 plus 4, and that is x to the 7th power. Okay. Now let's say I have 7 times n, and I'm going to raise that to the 4th power. Oh, good. This reminds me, there is one that I need to cover before we do that example. All right. So let's look at 3 times, and we'll do the variable x raised to the 4th power. Okay. So pretty similar to the other example that we're going to do. All right, so let's work this out. This is 3 to the x. Oh, I'm sorry, 3 times x times this is our base. 3x is our base, and we're going to multiply that base 4 times. 2, 3, 4. Obviously, I don't need those dots. That's kind of redundant. They're already in parentheses, but you get the idea. 3x times 3x times 3x times 3x. There are no terms here, nothing to distribute. It's all factors. It's all things we're multiplying, so we can multiply all those out. 3x, 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 3x. Everything's being multiplied through. So I can multiply things in any order I want. So I'm going to rearrange this a little bit to kind of make my point. So I'm going to put the 3's together. 3 times 3 times 3 times 3, and then times x times x times x times x. So notice that we have 4 3's being multiplied together and 4 x's being multiplied together. Okay? So this is 3 to the 4th power times x to the 4th power. So what we see is that if I have two things, a times b, raised to a power n, this n gets distributed, as long as this is multiplication, that n gets distributed to both factors, a to the nth power times b to the nth power. A to the nth power times b to the nth power. So let's add that one here. A times b raised to the nth power becomes a to the nth times b to the nth. All right, good job. So now let's go back to that example that we started with. So we know that we can distribute this 4n, and this becomes 7 to the 4th power times n to the 4th power. And you can write this number if you want. You can do 7 times 7 times 7 times 7. For time's sake, I'm not going to do that just so that we can get to some other things. All right. Okay, let's do another example. We have 3x squared to the 5th power. All right. So what do I do here? Well, the first thing I notice is that I can do this property right here, okay? This n I can distribute into there, okay? So if I look at that, this is 3 to the 5th, but notice that I have a 2 here already. So what do I do there? Well, you know that if you have something raised to a power, you multiply if you have a power raised to a power. So in this case, this 5 comes into here, and you have x to the 2 times 5. So this would be 3 to the 5th power times x to the 10th power. And if you're curious and you want to kind of prove this to yourself, what you can do is take this right here and multiply it out. So this would be 3x squared, 3x squared, 3x squared, 1, 2, 3, 3x squared, that's 4, and 3x squared. And you can see quite easily here, once you drop all the parentheses and group all your things together, that you have 5 3's, and then you have 5x squareds. So your 5 3's together is pretty easy, 3 to the 5th, but your x squareds, you have the same base here. So we can add up all of these exponents, 2 plus 2 plus 2 plus 2 plus 2, 2, 4, 6, 8, 10. We'd see that. And you could even go further. You could take this x squared and make that 2 x's. And count up all of your x's, and you would have x to the 10th. Okay, let's work another good example. Here we have 5y to the 4th over 5y to the 4th. Okay. Now you can see, since we have identical factors, that that's just going to be a 1. But if we wanted to go ahead and kind of work this out, 5 over 5 would just be 1 times y to the fourth over the y to the fourth is y to the 4 minus 4. So that would be 1 times y to the 0, which would be 1 times 1, which would be 1. Hold on just a second. Sorry about that. Okay, let's do another example. I'm going to have negative 5 n to the fourth times n to the fifth. Okay, how would I work this one? All right, well, the negative 5 is not the same base as the n and the n, so I'm just going to leave that alone. And that's multiplied by n to the fourth times n to the fifth. Those do have the same base, so I can add the exponents. That gives me a negative 5 n to the 9th power. Okay. All right, so now let's start combining some different exponents together. Okay, so or different variables. So what I'm gonna do is x to the fourth times y to the third times x squared times y. Okay, so what is that? Well, I can order multiplication in any order I want. If you remember, a times b is the same thing as b times a. So what I'm going to do is I'm going to put my x's together and my y's together. So x to the fourth times x to the second times y to the third times y. So this x and this x are the same base, so I can add those exponents. X to the 4 plus 2. And then my y's, I have y to the third, and then I just have a y here by itself. Remember that the y there by itself, any variable by itself, has an implied degree of 1. So this is going to be y to the third times y, which is going to be y to the 3 plus 1. So I'm left with x to the 6th power times y to the 4th power. Okay. Now let's do x to the third times y to the 4th over y to the second times x squared. Okay. So here I have factors on top, factors on bottom, and I notice I have x's and y's. So right now I'm going to look at just my x's. I have x to the third over x squared. So that's going to be x to the 3 minus 2 times I have y to the fourth over y squared. So that's going to be y to the 4 minus 2. All right. So that's going to leave me with 3x to the third minus 2. 3 minus 2 is just 1. So I'm just going to write x times, and then 4 minus 2 is 2. So y to the second power. All right. Now I'm going to do x to the third times y to the fourth raised to the second power divided by y to the third times x. Okay, we're going to get a little bit more complicated here. All right, so I don't want to come in here and just do y to the fourth over y to the third, because I have these parentheses and the exponent on the outside. So I want to make sure that I'm dealing with something like this, where I have the individual variables with their exponents, okay? So we need to square this first. So I'm going to distribute this 2 in there according to one of my properties. If I have things multiplied raised to a power, I can distribute that power or that exponent inside. So this is, and then since they already have exponents raised to an exponent, we're going to be multiplying. So this is going to be x to the third times 2 times y to the 4 times 2 divided by y to the third times x. 3 times 2, that's x to the 6th power. 4 times 2, that's y to the 8th power, over y cubed times x. Okay. Y to the 6th over x. I'm sorry, x to the 6th over x. So this is x to the 1 power. This is going to be x to the 6 minus 1 times, I have y to the 8th over y to the 3rd. So that's going to be y to the 8 minus 3. So that leaves me with x to the 5th power times y to the 5th power. All right. Let's do x to the negative 3rd times y squared raised to the 3rd power over x to the negative 2 times y, all raised to the negative 4th power. Okay. I'm going to take this 3 and multiply it in. This is going to be x to the negative 3 times 3, and multiplied by y to the 2 times 3 over this negative 4, we're going to multiply in. This is x to the negative 2 times negative 4 times y. Y by itself is just a 1 times negative 4. All right, so x to the negative 3 times 3 is x to the negative 9. Y to the 2 times 3, y to the 6th, over x to the negative 2 times negative 4, it's x to the positive 8. Y to the 1 times negative 4, that's y to the negative 4. All right, now if I have a negative exponent, then I'm going to take it, this x to the negative 9, I'm going to move it down to the bottom. So I have y to the 6th up here. And then when I move that x to the negative 9 to the bottom, I have x to the positive 9, x to the 8th, y to the negative 4. That y to the negative 4, since it has a negative exponent, I can move it to the top. So I have y to the 6th, y to the 4th, over x to the 9th, x to the 8th. So equal bases, I multiply together with different exponents. I can add those exponents. y to the 6 plus 4 over x to the 9 plus 8. So this is y to the 10th over x to the 17th. All right. Let me work one more example for you. Let's do negative 2x to the 4th times y to the negative 3rd times z to the negative 3rd over the quantity of z times y to the negative 4th end quantity raised to the 0 power times quantity 2 x to the negative 2 y to the negative 2 z to the 3rd, and that quantity raised to the 3rd power. All right, it's a pretty hairy one, okay? But immediately we can say, hey, this quantity right here raised to the 0 power, this whole thing raised to the 0 power, that's just the number 1. So that's pretty easy. So let's just go ahead and do that. 2x to the 4th, y to the negative 3rd, z to the negative 3rd over 1 times 2x to the negative 2, y to the negative 2, z to the 3rd to the 3rd power. Okay, let me switch colors here so we can kind of keep everything clear. Since I have parentheses here, I'm going to go ahead and distribute this third since I have no addition or subtraction. So that'll go to the 2, the negative 2, the negative 2, and the 3. Okay, so we will have negative in the numerator 2x to the 4th, y to the negative 3rd, z to the negative 3rd. We haven't done anything up there. Then here in the bottom, we're going to have 2 to the 3rd power because of this 3. X to the 3 times negative 2, negative 6. Y to the 3 times negative 2, negative 6. And then z to the 3rd, raised to the 3rd. That's z to the 3 times 3, which is 9. All right. It's going to be equal to, I'll have my minus out front. Okay, 2 to the 1st power over 2 to the 3rd. That's going to be 2 to the 1 minus 3. Okay, and we have x to the 4th. This y to the negative 3rd we're going to put down here. This z to the negative 3rd we're going to put down here. And then these two here, the x to the negative 6 and the y to the negative 6, we're going to move up here. So up here we will have x to the positive 6 and y to the positive 6. Underneath, we're going to move this y to the negative 3 down. So we have y to the positive 3rd. We're going to move this z to the negative 3rd down. So we have z to the positive 3rd. Now, that z to the 9th is still down there. Now, this 2 to the 3rd is not here. Because remember, what we did here was we did 2 to the 1 minus 3. Okay, so it's captured right there. So 1 minus 3, of course, is 2 to the negative 2. So our next step will be to move that down. But in here, we can combine these two because we have the similar base. 4 plus 6, x to the 10th, y to the 6th, over y to the 3rd. Here we have z to the 3rd, z to the 9th. 9 plus 3, That's z to the 12th. Okay. We're going to move this 2 down to the bottom. Oops, forgot my negative out front. Negative out front, the top, I'm just left with x to the 10th, y to the 6th, 2 to the positive 2 now in the denominator, and y to the 3rd, z to the 12th. Now this y to the 6th over y to the 3rd, that's going to be y to the 6 minus 3. So that's going to be y to the 6 minus 3 is y to the 3rd. So x to the 10th, y to the 3rd over 2 squared, z to the 12th. And that's my final answer. All right, I'm going to try to get this edited and uploaded tonight so that you guys have this to go back to, because I know this is a little bit hairy, so that way you can kind of see the examples worked out again. We are 3 minutes over our time, so that is class for tonight. We'll see you guys tomorrow night.
Thank you. Bye.
Thank you.
Thank
Bye.
you.